social studies class since like
It's like, you know,
the beginning of my junior
It's
year.
not rendering.
Not gonna lie, I prefer that than trying to jam in your seat.
Yeah, it's my least favorite subject, so I don't really love it. Huh?
You think about teaching history is that it's not really changed.
Yeah, exactly.
It's like, okay, guess what, the Japanese still have a little heart.
Still same thing.
They're just like, oh, hey, in physics, oh, we found dark matter. Okay, well, let's rewrite it.
Yeah, now you have to rewrite your whole recipe.
Yeah. I mean, it's like, seriously, how much has history changed since you were teaching it in the 1970s? What has changed? Gee, there was still the fall of the Roman Empire.
it's just motion.
Okay, all right.
So weird.
The wiggling pencil.
Yeah,
Got the wiggly.
yeah, okay, it's kind of, okay.
Wait, I went out and bought new pencils for your class, and I never used them until I took this class. And then my one trusty pencil I had in the bottom of my pencil bag ran out, so I had to go buy some new ones for this class.
So did you buy the old style, like where you sharpen them, or are they mechanical pencils? I like those. Okay. Yeah, I can't do the wood ones.
No, I don't like them.
Okay, enough. Brandon talks about this. Okay. So let's start with the calamity of cart motion. Okay. So hopefully this is the YouTube video that's out. Okay. That's the one that I introduced on Friday. So you guys are going to collect the data. I'm going to use the data that the group collected on Friday. So here's the short version, is that you're going to push the cart against the wall. You're going to have a mark at 1.5 meters. Here's 0. Okay. It's going to roll in, it's going to hit the wall, and it's going to bounce back. And you time each, and you're going to time each intervals. Like Ryan might time from here, from 0 to 1.5. Lauren's going to time from 1.5 to the wall. Amanda's going to time from 3 back to 1.5. Adam's going to time from 1.5 back to 0. Josh is going to time the entire event. Okay? So that's the data that you're going to need. So here's what's going to be most critical. To calculate the velocity in each interval, we're going to take the displacement, and listen to me, it's the displacement, not the distance. Displacement is a vector quantity. So your displacement is going to be P minus P initial. So like on the way in, your final position is going to be 1.5, your initial position is going to be 0. Then you're going to go from 1.5 to 3, then you're going to go from 3 back to 1.5, 1.5 back to 0. So what that means is that your displacement vector is going to change sign, okay? Because they're going to be pointing in, going towards the wall, and they're going to be pointing back. You're going to change direction. So when you change direction, what 3 things has to happen? You got to slow down, stop, change direction, and then speed back up, okay? Which means your position time graph has to break over center, which means your velocity time graph has to go through 0. So your position time graph won't give you too much trouble. So if you look at the data that they collect, you guys are going to get your own, but yours is going to be pretty similar. So like on Friday, their group took 2.70 seconds for it to hit the wall. I think their time was like, I don't know, 1.20 and 1.50 seconds. Okay, I don't remember the exact numbers, but it was like 1.20 seconds to get to here, and then it was like another 1.5 seconds to get to here. It took a little bit longer because the cart was slowing down a little bit as it rolled. So here's what's going to be important. How you calculate the velocity in each interval is you're going to take that displacement and then you're going to divide it by how long it took. So what we're going to assume is that we have constant velocity over this interval. Now in reality, this cart's going a little bit faster when it starts here, and it's going a little bit slower when it crosses 1.5. But this is kind of give us just an idea of how fast it's going. The same thing is going to happen here. We're going to take 3 minus 1.5 to get our displacement, divide that, that's going to be this. Now, what is most critical is that elapsed time when you're going to cross the x-axis on your velocity time graph, which means the cart is at the wall, which means the plunger is fully compressed, okay? So when you add those two intervals together, okay, whatever you get for the first, whatever you get for the second, you at home, you have 2.70 seconds. So that means that's when your position time graph is going to be at 3 meters. So what you guys get for your data, listen to me very, very carefully, what you guys get for your data is going to be this 2.70 seconds. That's when it's going to break over, that's when your position time graph is going to break over center. Now, what will give you most trouble, I'm going to tell you right now, is your velocity time graph, okay? This is a running clock, okay? This is a running clock. So, when you find 2.70 seconds, or whatever it is for your data group, okay? Get a 2.70 seconds, that's when this thing has stopped. That's when that plunger is fully compressed. Then come down here to this velocity time graph, and that's when your velocity time graph has to go through 0. Because listen to me, both graphs have to show the same thing happening at the same time, okay? This is what's absolutely vital. So, whatever your sum of your first two intervals is, you, red or white group, this is your data. You're going to go to 2.70 seconds, and that's when your velocity time graph is going to cross through 0. If you add your times together and you guys get 3, that's when your guys is going to cross through. That is the most vital bit of data. Now, down below, okay, down below, about 3/4 of the way down the page, we're going to figure out when the plunger hit the cart. Because this is when it was fully stopped. So it took some time for that plunger to hit and compress. It takes about 1/10 of a second, about like that. And then once it's fully compressed, because Mother Nature hates stored energy, Mother Nature likes kinetic energy, then Mother Nature goes, hey, I'm going to take that spring, I'm going to make it expand, and then it's going to push back. So to get when it hit, and this is what this is down here. So you're going to subtract 1/10 of a second, and then you're going to add 1/10 of a second. So for you guys at home, you're going to come back 1/10 of a second, and you're going to be like at 2.60 seconds. And then you're going to add 1/10 of a second, and you're going to be out here at 2.8. So this interval from 2.6 to 2.7 to 2.8, this is when you're going to, this is when the action is happening. This is when the cart is hitting, it's compressing, it's fully stopping, and it's pushing that thing back, okay? So what I would recommend doing, and this is going to flip you all out because you all are used to playing connect the dots on graphs, and you're very good at playing connect the dots on graphs. We don't have all of the dots. We're going to have to extrapolate some data. So what I would do, for now, I'm just going to sketch in this line. So I'm going to go, I know I'm here, okay? I know I'm going to be at 2.7, and I know I'm going to be at 2.8. So I kind of got an idea of what this line is going to look like. Now, let's just say that your first interval velocity was 1.1. I'm just making up a number. But here's what you want to think through. That cart is going to be going its absolute highest velocity at time 0. Okay? That's when it's going to be going its fastest. And then it's going to slow down a little bit. So what I would do is I'd say, okay, let's say this is 1 meter per second, and let's say that's 1.5 meters per second. So what I would do is that I would, let's say this first interval was like 1.20 seconds. So I'd come out here to about 1.20 seconds and go, okay, I know what the velocity is at that point. Okay, so I'm going to have like a data point right there. Then I'm going to know at that second interval, I'm going to have that second velocity during there. So I'm going to have like another data point. So what I would do is I would draw this as like a sloping line. Because think this through. So at time 0, you have your initial highest positive velocity. You don't know what it is, but it was probably going a little bit faster than you know, it was slowing down a little bit. So you're going to know a couple of points here in time. Just slope that out, have it hit here. I don't know what the initial velocity was instantaneously at the beginning. I don't know that, but I know kind of how fast it was going, and then I kind of know how fast it was going in that other interval. So this is where you kind of have to play connect the dots. And then out here, you're going to know two other negative velocities, okay? So you got a negative velocity at some point in time out here, and another negative velocity at some point in time out here. So when you get done, this graph is going to look something like this, okay? So this is when it's crossing the beginning. It's slowing down a little bit. It's going to hit the wall. Bam! The plunger is going to compress. That's what's going to make it slow down. It's going to fully stop. That spring is going to expand, which is going to make it do this. This is when it's going to leave the wall, and then it's rolling, and then it's slowing down as it comes back. Okay? So this is roughly what your graph is going to look like. Okay? When you get done, this is what it should look like. Here's what you cannot do. Okay? Do not do this. Do not go to 2.70 seconds and then draw the line out here to this third data point. Okay? Because otherwise, you're going to make it look like it took that plunger about 3 seconds for it to expand. And it didn't. That thing expanded just like that. So, you're here. It's going to hit at 2.6 seconds. It's going to leave at 2.8. And you're going to be here at 2.7. Now, there's a whole bunch of stuff that you have to do on that graph that's listed down below. Indicate the sign of the velocity, indicate the sign of the acceleration, tell me if it's speeding up or slowing down, when the plunger hits, when it expands, when it compresses, and when it leaves. So draw, especially if there's ever a graph that you draw big, in terms of especially the vertical scale, this would be the one, okay, because you have so much to label on here. Now, when you're labeling velocity and acceleration, don't come in here and go, oh, put positive and positive, or whatever it is. If you just put two positive signs, I don't know what that means, okay? I don't know if you're talking about velocity, I don't know if you're talking about acceleration. So if you think this has positive velocity, put positive V. If you think it has negative acceleration, put a negative V. So you're going to have 1, 2, 3, 4 distinct regions to label velocity and acceleration. So I want to know what's happening here, what's happening here, what's happening here, what's happening here. Okay? So 4 distinct regions of velocity and acceleration. Let's just make sure everybody's clear. Up here, what's the sign of my velocity? Positive. It's slowing down, so what's the sign of my acceleration? Negative. Here I still have negative acceleration, but now I have, but I still have, so therefore I am slowing down. From here to here, now I have, but I also have, no. I have negative velocity and negative acceleration, therefore I am, and from here to here I have positive acceleration with, therefore I am slowing down. So, force equals mass times acceleration. So, if you're going to change the acceleration, you change the force. So, here I have a very small negative acceleration because I have a relatively small negative force. Here I've got a much bigger negative acceleration because the plunger has hit the wall and I'm exerting this huge force. Here I still have negative acceleration. This is the only place I have positive acceleration. So on the back, on all those questions on 2 through 6, make sure that you're very specific when you answer those questions. Just don't say, oh, when it's at the wall. There's a whole bunch of things that are happening when it's at the wall. Okay, a whole bunch of things. When you get to number 7 and number 9, you want to calculate the area. This is what I would recommend. I would come in here and treat this thing like a rectangle. when you kind of come across like this, you leave some off the top, but you like to pick it up over here. So you're going to know how to draw a line that splits this and call this your height, okay? And then call this your width. And then you're going to do the same thing over here. I'd come over here and have like maybe a line kind of like this, where that becomes a rectangle. Now, you can do like, you can find this triangle, you can come across like this and find this triangle by itself and then the rectangle up there. If you're really hardcore into geometry, hey, knock yourself out. If you just want to make it simple and kind of say, well, here's kind of the average line, but what you have to be careful of, when you're doing this time has to be from here to here, okay? Don't use the entire time. It's only from this point to this point, okay? That's what you have to be careful of. When you get to number 13, okay, on motion diagram and velocity vectors and acceleration vectors, draw these at 4 points. So what I want on number 13, and do this on another sheet of paper, do not try and cram number 13 in here. So you're going to label this, so on, you can just call it on the way in, okay? And then you're going to have compression, and then you're going to have expanding, and then you're going to have rolling back. So what I want is velocity vectors and acceleration vectors, okay? Even though you don't know the actual acceleration, draw them as a relative amount in the correct direction. So let's say that you want to define on the way in as being in this direction. So here's like V1, okay? As it rolls, what's going to happen to that velocity vector?
It's gonna shorten.
But is it going to shorten a lot?
Not really.
Not really, okay? You're pretty low friction, okay? So maybe draw this one just a little bit smaller, okay? Now, if it's getting smaller, it means it's slowing down. Which direction is your acceleration vector going to point?
In the opposite direction.
Opposite direction. So I'm going to maybe draw this as some small negative acceleration, okay? Now, when it hits, it's going to hit with some V1. But then rapidly, what's going to happen to that velocity vector? It's going to get real small real quick, okay? So then on that one, maybe draw that one as V2, okay? So this is going to shrink really fast because that plunger is hit. So which direction is my acceleration vector going to point?
It's still negative.
Still negative, but now it's going to be a big negative. Because now you're making this thing slow down really, really quickly. So that's going to be a big negative acceleration. Now, on the expansion side, so if you have it going in this direction, going in, then which direction are these vectors going to point? They're going to be pointing
Yeah, that way.
that way, but then it's going to be speeding up or slowing down.
Speeding.
Speeding up. So then you're going to draw like a small V1 and then draw a bigger V2. But then, now my acceleration vector is going to be pointing in this direction. Okay? So, this is going to be one of the most important things that you have to understand. When I'm talking about acceleration, you have to get out of your minds right now that acceleration just means speeding up. If this velocity vector is changing in any way, shape, or form, in magnitude or direction, you're accelerating. Okay? Now, here's what I want you to understand. This motion here has to correlate with what's happening on your velocity time graph. So if you have a shallow negative slope here on your velocity time graph, you're going to have a small acceleration vector down here. If you have a big sloping line here, meaning your velocity is changing rapidly, you got to have a big negative acceleration vector down here. Okay? So this is what I'm looking for. Now, and this is going to be important in terms of the second line. If you want me to think your velocity vectors are changing, you draw them so that I can look at them and tell that they're changing. If you think they're the same, you draw them the exact same length. I am not going to take a ruler and try and guess if you think they're the same or if they're changing. Okay? So if you want me to think they're changing, draw them so I can clearly see that they're changing. Okay? So that should get you this. Tomorrow, this lab, both of these labs aren't due until Wednesday. Tomorrow at the beginning of the class, I'm going to answer any questions anybody might have, either the white group or you guys. So if you guys get to this point, because it isn't due tomorrow, this is why I'm having this lab due on Wednesday. So tomorrow, at the beginning of the class, if you guys want to zoom in and you hey, camp, I still don't know how to answer a question. You can ask me tomorrow, because this is why I'm not making this lab due until Wednesday. Okay? So, right away, as soon as I get done, you're going to go back and you're going to get the data for that. Okay? So, let me go get the other piece of equipment that you're going to need. Okay. So, the other bit of data that you're going to do, other lab that you're going to do, well, they've already seen it. Yes, have it. So, what you're going to do, you all at home have already seen this. I'm doing this for the people that are here. So I'm just going to push the cart up the ramp. So you can take this, give it a push, okay, and have it go up there quite a ways, and then come back down. So you're here, going, come back down. Now, do not include the push, okay? Don't include the push. You're going to start this analysis from the point that you let go of it until it gets back to this point. So you want to have somebody keep track of where the front of the cart is when it leaves your hand, and then you want to keep track of when it gets back to that point, and you want to time the entire thing. So I'd have, there's probably three, yeah, we can have three groups. So I'd have, you want to have one person timing it, or at least two people timing the entire event. Don't time it up and time it on the way down like we did with the spring cart lab. You're going to go from here and time the entire event and then until it gets back to that point. So, here's the data that you're going to have. So here's the ramp. Let's say that the front of that cart was at, I don't know, 0.12 meters. That is marked off in centimeters. Y'all can do the conversion into meters. And let's say that the top ended up here at 1.14 meters. What you have to be careful of is that if you're going off where the front of the cart is up here, you have to watch where the front of the cart is up here. You can't go off the front of the cart here and then watch the back of the cart when it gets up there, or you're going to be off by the length of the cart. Okay? And let's say that this total time was, I don't know, 4.8 seconds. I'm just making up a number. Okay? So here's what's going to be important. You're timing the entire event. So what we're going to assume is that this thing is symmetrical because it returns back to the same point. Okay? So, the 4.80 seconds is from the time that you let go of it until the time that it gets back to this point. Okay? That's the entire thing. Now, on your displacement on the way up, remember that's P minus P naught. In the lab, I explicitly tell you, I want to see this calculation because everybody's data is different. So on the way up, my final position would be 1.14 meters. My initial position would be 0.12. So I'm going to take 1.14 minus 0.12. So on the way up, my displacement is 1.02 meters. The time up is going to be half this time, which is going to be 2.40 seconds. Now, here's what I cannot do. Do not take 1.02 meters and divide it by 2.4 to get the velocity. Okay? You can't do that. This thing is accelerating in a big way the entire time. When you push the cart along the floor, okay, that was relatively constant velocity. It didn't change much until it hit the wall. This one, you are accelerating the entire time. So on the second lab, do not take your displacement and divide it by the time to get your velocity. Do not do that. Because this is acceleration. Now, On the way down, and this is going to be important, on the way down, you're here, and then it's going to roll back down. So this is one of the most vital things that you have to get. You're going to start with some positive velocity vector pointing up the ramp. Now, as it rolls up the ramp, what's going to happen to that velocity vector? It can do one of three things. It's either going to stay the exact same size going up, it's going to get smaller on the way up, which would be cool, excuse me, or it's going to get bigger, which that's the one that would be cool. If your velocity vectors were getting bigger on the way up, that would mean it would be going faster. It's like you push it up the hill and it goes faster. Okay? Kicked in the rocket engines or something.
Yeah.
Yeah, cool. Don't get me wrong. So what's going to happen? Are they going to get bigger, smaller, or stay the same? Small. So this is one of the things that you've got to do on the last page of the lab. You're going to draw some velocity vectors. Okay? So if you call this V1, guess what? When you draw V2, what are you going to make it?
Small.
Smaller. Then you're going to draw V3, and that's going to be
Small.
even smaller. So which direction are my acceleration vectors pointing? Down the hill, right? Okay, everybody's cool with that. Now, let me explain the entire purpose of why I have every thought that governed me when I wrote this lab, okay? The whole purpose of this lab isn't about what happens on the way up. The purpose of this story is what happens on the way down. So on the way up, it fits in your wheelhouse. You're going, oh, we have positive velocity and we have negative acceleration. We're slowing down. That is in your wheelhouse, okay? That is in your comfort zone. You all can handle that. Oh, negative acceleration, I'm slowing down. I like this. It's cool, right? But here's what you want to do. You want to, on the way down, go, oh, it's speeding up. Therefore, I need to have positive acceleration because I'm speeding up. Because you all associate, at some level, negative acceleration with slowing down and positive acceleration with speeding up. The whole purpose of me writing this lab is to smash that idea. Okay? Now, on the way down, which direction are my velocity vectors going to point? Down. Makes sense? It's going down. My velocity vector should point down. But what are my velocity vectors going to be doing? Getting bigger. So if I have negative velocity vectors going down the hill and they're getting bigger, what has to happen to my acceleration vectors? Which way are they going to point? Down the hill, right? Now you're going to have negative acceleration going down the hill, but guess what? You're also going to have negative velocity, so therefore you're going to be
Speeding up.
speeding up. Okay? So that's what I'm trying to get you to smash through. The whole purpose of this lab is to look at what happens on the way down. I'm not worried about on the way up. You all can handle that. It's what happens on the way down. Now, you're going to make a sketch of a position time graph. Okay? Now, in this one, that would be like 4.80 seconds. Here we are at 2.4. It's just going to go something like this. You know you're going to start at 0.12 or wherever you started. Okay, you're going to know your initial position. You're going to know your final position is going to be 1 point, however far it is up on the hill, and then comes back to that point. So you're going to know at this point, what's the velocity of the cart?
0.
0. Why?
Because it stopped.
Yeah, and you're changing direction, right? Your tangent lines have a slope of 0. Okay, you're at a relative maximum if you're a math nerd. Okay, if you cannot change direction without stopping, I don't know how you understand it, but there's a whole bunch of different ways. Now, on the way down, what are you going to start to do? You're accelerating again, but now your lines are becoming steeper with a negative slope. So this is just going to be a sketch. Okay, that's all it is. It's just a sketch. You don't know the exact points in time. It's just a sketch. Now, this is where the absolute magic happens. But this is going to flip you out initially because you all are nerds. And I feel your pain. Okay? Your velocity time graph, you're going to draw it, but you're not going to know the data points. So you're going, blasphemy, Berkeley, blasphemy. But it's going to be cool how it's going to work out in the end. Okay. So here's going to be your velocity time graph. Is your velocity time graph going to start at 0, 0?
No.
No, because we don't include the push. Okay? So what you do know is that there's 2.40 seconds, and there's 4.80 seconds. So this is going to be boring, but you're just going to come up here and you're just going to make a mark. You don't know what the initial velocity of this thing is. Okay, this is what's going to flip you out. It's like, we have to draw a graph and we don't know where it starts. You don't. But you're going to find out, and that's the cool thing. So, you're going to go from here, like this. Okay? That's it. That's what your velocity time graph is going to look like. That's it. Okay? You're going, well, how do we find this? Ah, yes?
No, I know how.
Well, hold on. Okay, so here's the deal. What does the area on a velocity time graph give you? Displacement. So area is going to be my displacement, which I know because on the way up I know my initial position and I know my final position. So I'm going to know my displacement from the front of the lab. Okay, I'm going to know this number. Now, this looks surprisingly like a triangle. How do you find the area of a triangle?
1/2 base times height.
1/2 base times height. Oh, now, the area is going to be your displacement. You're going to know that number because you know how far up it went. Okay? You're going to know the base because you know how long it took to go up there. Okay? And we're assuming that we have uniform acceleration. The height is going to represent what? Your initial velocity. So we're going to use the area of a triangle here to determine the initial velocity of the part. Okay? That's what I said. It's cool at the end. Now, on this lab, in any lab, the purpose of this lab is not about crunching numbers. The purpose of this lab is to convey to me that you know what's going on. So, solve this equation for h. Multiply by 2 and go, oh, 2a over b is going to equal my height. Okay, so over here on page 2, wrong one. On the application of the terrible triangle, where you've got, on number 16, use the area of a triangle, okay? Solve for h, which will equal the initial velocity on the way up, and you're going to get that number. So, in this case, I would like take 2 times 1.02 meters and then divide that by 2.40 seconds. That's going to get me my initial velocity, okay? That's going to get me this height. Now, the next thing you want to do is calculate the acceleration. There's 2 ways that you can think about acceleration. I don't care how you think about it. This is up to you. If you are a slope-intercept kind of person, you have 2 data points. You have 0 and whatever that initial velocity is, and then you have another data set of 2.40 seconds and 0 meters per second. So if you're a slope-intercept person, you have 2 x coordinates, you have 2 y coordinates. Find the slope of the line. Now, clearly, what's going to be